Today, it's another EuroCC seminar series. Thank you, Daniel, for being here. Daniel will talk about towards exascale physically based computational hydrology. Dr. Daniel Caviedes Uyeme is a computational hydrologist. He's a team leader of the simulation and data laboratory for terrestrial systems of the ULIC Supercomputing Center. He obtained a civil engineering degree from the University of Costa Rica, an MSc in applied mechanics, and a PhD degree from the University of Zaragoza. He has previously held research and teaching positions at the University of Zaragoza, University of Sheffield, and BTU Cottbus Senftenberg. Okay. His research is centered around high-performing, performance-portable, and scalable numerical solvers for hydrodynamics and hydrology, and their application for hydraulics and hydrology across scales, both for natural hazards as well as eco-hydrology and landscape function. I hope you find this talk interesting, and afterwards there'll be some time for you to talk to the presenter as well.
Okay. So firstly, thanks for the invitation. It's very nice to be here in this sunny weather. It's lovely. It's a good change after a few weeks of darkness. So do keep me in check with time because I have no clock to see. So it's yeah.
Just proceed as normally.
Yes. All right. Okay. So let's get a move on then. Okay. Let me start with what I believe are the take-home messages from this talk. One point I want to make quite strongly is that we can really do hydrology based on hydrodynamics. I mean, in the end, hydrology is nothing more than figuring out how much water there is, where it's going, and how fast. And this is driven by basic mechanics, let's say. So contrary to what has been done in the past, where the dynamics having a bit ignored, mainly because of computational constraints, this is very much relaxed these days. The advantage of that is that taking this physically based approach allows us to cope with the multiple scales that are of interest, to capture the pathways, to capture the connectivity of the fluxes that we have, the travel times of the transport, and all of these wonderful, interesting processes that actually drive how nature works. Now, it comes with a huge cost of computational effort, but essentially we have the machines ready to go. The question for a long time has been, do we have the codes ready to go? And I think the answer to that is now yes. But overall, it's a community and a field that is still catching up with the use of high-performance computing, unlike, let's say, other fields in which it has been common for decades, like meteorology, for example. But it's catching up, and that's essentially the point that I want to kind of convey with the talk. Now, if you will allow me first a very short historical digression, especially for those of you who are not into hydrology, of why this is a bit of a paradigm shift and potentially a game changer in that sense. I really like to go back to this 1969 paper from Alan Fries and Harlan, where they came up with the idea that you could have a fully mathematically described and physically consistent hydrological model that encompassed the flows that you had on the surface, or I'm not sure if this is a pointer. That is a pointer. Yes, the stuff that you would have on the surface, stuff that you would have on the subsurface, and connect them seamlessly, essentially through the best physical description that we can have of these processes. And of course, you can put this on a grid, and obviously you can use a computer to solve whatever equations you write. The problem, they said, is, in the 1960s, they could afford a 100 by 100 by 100 cube and not more. And if you imagine that if you wanted to, for example, solve the entire hydrology of Cyprus, well, that's kind of a very coarse, very bad resolution. And they ask, very interestingly, what of the machines of the 1970s? We can ask right now, what of the machines of the 2020s, right? And that's a bit of what the talk is also about. They also pointed out very aggressively that the runoff process is extremely complex and cannot be described in a mathematical way. I would challenge this assertion these days, and they specifically say that the direct use of the shallow water equations to represent the surface flow would not lead to significant improvement in rainfall and runoff models. And this is something I think we can now challenge because we can actually compute it. So they made this conjecture, but we can actually test for this. Now, in the past, hydrology has been mostly done with so-called lumped cascade models, which break the landscape into catchments and subcatchments, and then essentially apply properties to these entities, these units, and compute fluxes of water going in, fluxes of water going out, and how much stays in, and kind of has a mixer in to represent the different processes. Now, this has the issue that, of course, you don't see a fully spatially distributed answer to your problem, nor does it actually capture the processes themselves, their representations, functional representations of the processes, but not the actual physics. So what I'm proposing is, we can essentially move away from this, and it's feasible. One such example is a model that's not my development, but it's something I contribute to in Jülich, which is the Parflow hydrological model. You see this follows the same blueprint as Fries and Haarland, and it represents the typical main driving processes in subsurface and surface flow in the landscape. Now, this is a code that is pretty mature. It's been around for about 40 years. It's been recently ported to GPUs, and it's been shown to be pretty much exascale ready. And my colleagues in Jülich, they use it for, let's say, quite applied, quite tangible concrete applications, such as providing quasi-operational soil water forecasts for farmers, for example. So you can reach this. This is a web page. It's unfortunately, I think it's unfortunately only in German. So that's the downside, but nothing that a translate app cannot solve. And you can basically inspect to a resolution of about 600 by 600 meters, what is the expectation of soil water for the next 14 days. So I use this to water my garden or not, mostly not because it's Germany. But it's also used within a larger idea, which is this so-called terrestrial systems modeling platform, which integrates atmospheric models, land surface models, and hydrology. And we use this at continental scale over a domain that is, let's say, what we call the pan-European domain. Operationally currently at 12-kilometer resolution, and it looks more or less like that. So what you're looking there is soil water on this area, let's say, of Central Europe, and we're moving towards 3-kilometer resolution. That's, of course, 4 times higher, 16 times more computational points, and also 4 times more time steps necessarily. You see the improvement, of course, especially around mountainous areas and river corridors. So this is where we want to go. We want to go even higher resolution, 1 kilometer, half a kilometer resolution, where we can actually provide information for managers and for farmers and things like this. Well, that's just a close-up of what's going on there. This is translated, as I said, into useful information that stakeholders can use. This, again, is not my work, but I'd just like to illustrate how this looks when you kind of go all the way, right? You develop the model, you put it on the supercomputer, and then you start using it to actually generate this information. You make it publicly available. The current targets, and this is also partially the reason that I'm invited here, is that within the Energy-Oriented Center of Excellence, or ECHO, we have the target to go to global scale simulations below 1 kilometer resolution. So what you see here are experiments from my colleague Stefan Collett using Parflow on a 1 kilometer global grid. It's, there's a lot of information in there. Just figuring out what to do with it is already a challenge. And the next target is to scale this up to let's say 200 meter or even 100 meter resolution globally. The challenges here are everywhere, pretty much. Okay, but I will go now down a different path, and I will talk a little bit about surface flow. And Parflow is mostly focused on subsurface flow. And in the past, again, one of the things that has happened is that these set of equations, are the so-called shallow water equations or Saint-Venant equations, have not been used to solve problems at hydrological scale because of the computational cost of integrating this highly nonlinear, complex, hyperbolic, conservative system. Then again, now we have a very mature solution to this, so it's actually feasible. And the flood modeling community, which has been traditionally the people who use these equations, also say, well, we can't use them because they're too expensive. So when this very interesting paper that came out a couple of years ago actually showed this, that people will still use one-dimensional and even simplified models because they cannot afford to use a two-dimensional representation and do actually what they would like to do. Now, That's kind of, as I said, just a historical digression. Now, another question that one might ask is, sure, so there's equations that can do this, and there's computers that allow you to compute it, but do you actually need to, right? Why should we use hydrodynamics for hydrological problems and hydrological scales? So I'll provide three arguments. The first one is that there's a multitude of scales that we want to capture. Then there are connectivity and connectivity issues and pathways that we have to represent in the models. Otherwise, water is moving somehow, but not necessarily how it's moving in nature. And there's transfer phenomena that is associated. So I'll try to make these points very, very briefly before I jump into what we're actually doing. Now, this is what the essential motivation, the problem behind this is this thing I call the hydrologist bad sandwich. And is that hydrology is there sandwiched between a highly variable atmospheric forcing in time and space and a highly heterogeneous surface and subsurface because of geology, because of soils, because of land cover. And somehow all of that is interacting in how processes actually emerge. Now, the argument in essence is that if we use hydrodynamics, we have these very fine scale information which we can upscale by using HPC, by using gridded representation of our models, while at the same time using more classical approaches from conceptual behavioral or phenomenological models, which we can downscale. And somewhere in between, we probably have a good set of tools. So I'm not proposing by any means that we should get rid of all this old, well-established knowledge, but we should actually try to blend them in together. I'm going to provide to you a few examples of why we need the hydrodynamics. One very obvious and easy one is flooding, and especially flash flooding. And you may remember from the summer of 21, there were severe floods in Germany. This was close to Jülich. Jülich is somewhere around here. For you to put it on the map, basically. And this is the best that the European flood warning system currently can do. Now, if you look at this, you will see that the pixels are very large. And everything that is marked in purple means extreme flash flood severity, which means everything, pretty much, right? So if you place yourself as a civil safety officer that has to make a decision, you might as well just call the day off and say, well, it's the end of the world, right? This is not actionable information. That's the criticism, but it's the best we currently have operational. Now, the reason for this, in part, is because of the modeling technology that underlies this warning system, which is one of these so-called lumped models, a thing called LISFLOOD. And I asked the question, well, what if we move into really using the depth integrated shallow water equations? Can we do any better? In terms of flood forecasting, for example, very briefly, one issue that we have is when we have this type of small flash floods, so let's say in essence small catchments, the data that our models are producing is very coarse and it's very qualitative. It's things like what I just showed, high severity, high probability, very dangerous, spooky monster, but not hard numbers. What is the water depth? What's the water velocity? How fast will the water get here? So we have qualitative data that's not very reliable, and we just get it a few hours before the event. Whereas what we would want to have is fully detailed two-dimensional hydrodynamic fields with reliable spatiotemporal information, high reliability, and a lead time of days so that we can warn the population, evacuate them, do whatever needs to be done. Now, why else do we need hydrodynamics? Well, because we're dealing with systems that are spatially very heterogeneous. Catchment might look like this. And when we start coarsening things, just by coarsening, let's say by a factor 4, we start generating effects on the response of the systems. So the point of these figures here, which are very involved, I will not go into the details, is that if we compute typical metrics like the maximum discharge that we may have, on one grid or another, we get different numbers with exactly the same forcing, with exactly the same parametrization. And in fact, what we realize, and we can do very detailed analysis of this, is that by coarsening the grid more and more and more, we're actually missing out on all the relevant information that we are looking for. So we need the hydrodynamics because at very coarse resolutions, we lose that physical information that is embedded in it. Of course, again, in flooding, it becomes very obvious that if we don't have enough resolution, we miss completely the timing of critical events like levee breaches and things like this. All in all, that means we need physically based models running on high resolution whatever that means, which is very problem dependent. But we want to do it at catchment and regional domains. So whatever that means is hundreds, thousands, tens of thousands of square kilometers. And we have ensemble weather forecasts which drive our hydrology. So in all, we have a very large computational problem, and we need to feed it into a supercomputer. Then the other argument that I wanted to make is the implications across scales. And let me try to explain this very briefly. One interesting behavior that we see, for example, with surface flow, is that if we put rain on a surface that has this kind of sinusoidal wavy surface that is illustrated there with a grayscale, and we provide different features to this microtopography, the same rain on the same slope, with the same infiltration properties, will produce fundamentally different behaviors. And these behaviors are the result of how these puddles here connect or disconnect. It seems very intuitive, right? Now, the thing is, if we go to coarser scales, or I should be more precise, if we go to larger scales, what we see is that the same phenomena that produces different signals is observed on real catchments. So if we represent catchments in such a way that we lose all the small scale or high frequency features, and compare them to simulating the same catchments by keeping those features, we see these differences appear. Let's see if I can manage this. They appear in particular at the beginning of the run of signatures. So we see this across the different scales. And what this tells us is that if we lose this information from the small scale features, from the small scale fluxes, we have an effect on the signal. And that effect may be non-negligible depending on the application that we want to do. I also made the point about connectivity. So I need to explain what I mean by this. If you imagine rainfall on a mountain to catchment, for example, you would get something that looks like this, some water that runs off and forms streams. And we can kind of cluster these blocks of different connected areas. So imagine here that every thing that you see in a different color here is disconnected from the other color. So a fish could not swim, kind of. That's the idea. And it gives us an idea of how connected all these flow paths are. We can summarize this in terms of this number of connected clusters or number of disconnected clusters. And it gives us a kind of an interesting signature of how the different streams are connecting, how the network is building, and how much of the area of the catchment is contributing to the runoff. And when we examine this across different resolutions, which you could also think of as different scales, you see that it actually matters quite a lot. If we look at the same rainfall event on the same catchment at the same time, at two different resolutions, we get characteristically different connectivity signatures. So you see here the curves, you see that the magnitudes are significantly different, but also the shape, the behavior is characteristically different. And you see the spatial patterns are characteristically different. Now, what is interesting of this is that the discharge signature that we may measure at the end of the catchment is perhaps not that different, but the way that the water travels to that point is very different. And if you're interested on transporting matter across these streams, think, for example, of sediment, or you could think also of organic matter, pollutants, then we're actually missing out on that information. So with that in mind, the question, of course, is how to move forward. Well, what I'm proposing is, of course, we want to use hydrodynamic models into hydrological models. And we need to run them on supercomputers because of the large computational costs associated. In particular, in what relates to surface flow solvers, there has been in pretty much always a lack of scalable and open sourced solvers. So this is just a bit of a summary. There's plenty of shallow water solvers out there. Some of them are open sourced. But until very recently, so pretty much until 2021, there was no highly scalable shallow water solver that you could deploy and massively scale on a supercomputer. The first one was really Triton. And the next one was what I will talk for the rest of the talk, which is this SERGHEI model, which we recently published in 2023. So what is SERGHEI? Well, first, it stands for this very long thing, Simulation Environment for Geomorphology, Hydrodynamics, and Ecohydrology in Integrated Form. It's kind of an ambitious project that is way beyond only, let's say, surface flow, but it means to integrate all the different aspects of the hydrological cycle, including transport and including the interactions with vegetation and agriculture. The first paper we published on this is what's here up on top, where we presented the concept and the shallow water solver itself. And very recently, so just a few days ago, we finally got the version 2 paper published, which includes the Richards solver. So we now have surface flow and subsurface flow in a manner similar to what Parflow does. Now, what is new about SERGHEI in this sense is also that we pile on top lots of surface-related processes. That means advection and dispersion of anything that may be dissolved in the water, so suspended sediment transport in particular, but also bed load transport, so all the little rocks and sand that moves on the bottom of the river, and also a Lagrangian particle transport module to track non-dispersive materials and large-scale objects. That's, let's say, from the domain science point of view. From the computational science point of view, the big novelty is that we rely on COCOS. So if you're not familiar with what COCOS is, it's essentially kind of a domain-specific language layer or in a portability layer, depending on the jargon that you want to use, which allows you to write one code that you can deploy on multiple hardware platforms without having to worry about changing, from C to CUDA, from CUDA to HIP or to SYCL or whatever other programming language you need to reach accelerators. So SERGHEI is now quite a mature project. We treat it very respectfully in terms of research software engineering and sustainability. So you will find it on GitLab, open sourced, very transparently. We show all the tests that we do, all our pipelines. So if you're curious, you can just go and hop in and see how we're maintaining this as transparently as possible. SERGHEI is also heavy benchmarked. So we really have tested it against, I will not say all available published benchmark problems, but I would say a good 90% of them. And they all perform very, very nicely. So we have good grounds to say the solver is really performing. And in terms of computational performance, it's very, very satisfactory. It's actually very, very good. So let me go through these plots with a little bit of time. On the left, I'm showing you here just very well-known dam break test problem. So this is something real that actually happened in France in the 1960s. A dam broke, and there were a lot of fatalities downstream. And it's commonly used as a benchmark problem. And we've computed it here in 2 supercomputers in Jülich on CPUs and on GPUs, and also on a workstation GPU. And the only point that I want to make here is that the scaling on CPUs is quite nice. And of course, the jump from CPUs to GPUs gives us essentially a factor 10 speed up from a full node to a single GPU. And from one generation to GPU to the next, we get essentially also a factor 2. And this actually holds, this is a bit of an old plot. It's a couple of years old, but I'll show you also some more recent plots. Now, of course, we can also scale across many GPUs and many nodes, which is what you have on the plot on the right, where this very simple circular dam break problem, which is just an analytical benchmark, it's supposed to scale very well because let's say it's a symmetric problem. It has all the good features. It scales actually very, very good to at least 128 GPUs. These are NVIDIA Ampere A100 GPUs. What happens if we test it on real catchments? Well, we also see excellent scaling behavior. So here you have the Jewel supercomputer in Jülich, the Summit supercomputer, which was recently decommissioned in Oak Ridge in the US, and also the Cori system, which I think it's Department of Energy in the US. The point I want to make here is that SERGHEI is meant to be performance portable, meaning that its performance features and its scalability features should transfer relatively well from CPUs to GPUs. And what we see on the scaling plots, especially those down here, is precisely that. So COCOS is delivering on its promise, and our implementation is harvesting on this idea, and we get very good performance portability. And so this was already the case 4 years ago when these plots were made. Now, what is SERGHEI actually solving? So I will not go a lot into the details of the math, but if this, gets you excited, let me know. We can talk about it more later. We solve a Godunov type explicit upwind first order scheme for the shallow water equations. And if this doesn't mean anything to you, it's an Euler scheme that pushes things in time and solves Riemann problems at the discontinuities of the cells. We represent data as piecewise constant on the cells, so there's no high order reconstructions or anything like this. It's kind of pretty simple standard finite volumes, with the exception of how we treat the numerical fluxes at the discontinuities, which is kind of involved. So what we use is Rho's approximate linearization for the Riemann solver with a twist. So as I said, I will not go into the details of this, but essentially what we do is that we linearize our flux in our equation through the Rho approximate Riemann solver, and then we augment the Rho Riemann solver by adding an additional wave. So these hyperbolic equations have wave propagation, and one of the waves that gets generated is because there's discontinuities in our cells, and this generates the equivalent of a contact wave, and this exists always in our solution because there is always a source term, there is the bed elevation that appears in our fluxes, and this introduces a mathematical discontinuity. If we treat this right, and we do, we get a very stable and very efficient numerical solution. And this was a big breakthrough in this community, I would say between 15 and 10 years ago. So this matured the models in a very, very significant way, and we elaborate on this essentially. So in the end, what we get is these shallow water equations that, they look spooky, but they're nothing more than conservation of mass and momentum. And we translate it into a finite volumes expression, which here is expressed in wave form, where these alphas represent essentially the wave strength of the fluxes, and these betas represent the wave strength of these source terms. And somehow this has to be well balanced so that we don't generate spurious waves and destroy our solution. So as I said, I will really not go into the details anymore, but that's what's underneath. In terms of the implementation, SERGHEI is a hybrid parallelized system, so it uses MPI for distributed computations across GPUs and nodes. But for the in-node, let's say for the shared memory parallelization, it relies on COCOS. And this means we can reach OpenMP to parallelize across CPUs in a node, or we can use whatever target backend language to reach the accelerators that we have in the machine. Currently, it features a very naive 2D blockwise domain decomposition. It looks like that. We're working on making this a bit more flexible because it's becoming a bottleneck. And we're also working towards having dynamic load balancing. As you will see in some of the simulations, this becomes super obvious that it's necessary because the nature of our simulations, water may be in one place at one time in the domain, and as it moves through the domain, the computations are moving, the weight of the computations is moving from one subdomain to the next. So this becomes kind of interesting. And we're also working in the direction of adaptive grids. Currently, we can only do, very boring fixed Cartesian grids. But this is in the works. Fancier stuff that we are testing out is mixed precision computing. So this has always been a bit of a Pandora's box in this field because we have these wet to dry and dry to wet transitions. Our cells dry out. So this is asymptotically our mass going to zero. And if we lose precision, we lose these, let's say, thresholds. So it's always it doesn't work very well if you do single precision, which would give us a boost of about 2x in terms of computational performance. But nevertheless, we try because it would be a nice thing to have. And the other couple of fancy things that we're experimenting now is the idea of malleability. That means changing the number of computational resources on the fly. That's not killing your job and restarting it with a new set of resources, but having your job running and just ask for the scheduler, hey, I need more GPUs, can I have them? And reshape your job, reshape the job around that. Last and in this list is the idea of having in situ analytics and visualization. For two reasons. One is because the amount of data that we're generating when doing catchment scale high resolution is humongous. So writing to disk is a bad idea, and reading from the disk is a bad idea. And then having post-processing scripts that are not as highly optimized as the code is a terrible idea. That's one reason. The other reason is that we run all of these things on the GPUs, but we usually have CPUs idle on the node, so we can exploit them to do these analytics. How does the code in SERGHEI look? Well, as I said, it's Cocos based. So if you're not familiar with Cocos, the idea is we abstract stuff like our two-dimensional loops that you see here into this Cocos directive, which is, I mean, it looks a little bit like a pragma, but it's really a C++ template in which we say the size of the loop, and we declare a lambda, but you see that the rest of the code remains the same. So the key thing is that if you have a well-structured code that's well-designed for parallelization, migrating from a C or C++ code to Cocos is really very easy. It's minimally invasive. Very nice. You have to be careful with a few things, though. When you call functions, for example, within regions that, let's see if I can get it. This parallel reduce is a parallel region that can possibly be executed on GPUs. So you have to be careful that you declare the functions that you call as functions that should be compiled for the GPU. Otherwise, you will segfault, things like this. But as I said, it's really little things that you have to be careful. This you have to spin up all the way. So you have templated classes and templated functions in your code. You have to be careful you have to remind yourself to put the right decorators in there so that you don't segfault. And it's very important because otherwise you'll spend a couple of days going crazy finding why it's segfaulting. Now, the other side of this is where do you allocate memory? If you're familiar with GPU programming, you know that a big issue that we have is if we allocate memory on the CPU, it's not accessible for the GPU and vice versa. So handling this is really annoying in the code. It clutters your code a lot, and it's very error prone because you typically get code duplication. But Cocos does a nice job of abstracting this by basically creating a data structure that is memory aware or aware of its own memory space, if you will, and verifies that the memory space in which you have stored the data or that you're writing the data into is consistent with where you are executing your code. And this is done at compile time. So at compile time, you will already know whether you've done a good job. So if you're interested on this, I'm happy to provide more details. The interesting bit about it is that when you look at your main code, so something like here on the right, it just looks like plain C++ code. There is no, complex data structures or any pointer, abstract pointer things that you may have to do when dealing with backend languages. Now, very nicely, we can extend this not only from, let's say, to reach the CUDA backend, we can also reach the HIP backend, and recently we've also reached the SYCL backend. So I'll show you some results of this. And these data structures, these so-called views, they are not limited, of course, to simple primitives like floats or doubles or integers, but you can do views of complex classes as well. So it's very highly flexible in that sense. Now, I guess I'm kind of preaching to the choir, but you're probably aware that there's an HPC ecosystem that exists on the one side and worldwide. The push is very large. We've broken the exascale barrier. There's now currently 2 machines running that are exascale capable, Frontier and El Capitan in the US, number 1 and number 2 in the top 500 list. But there's plenty more. Of course, there's still 2 European systems in the top 10 as of November. But the point I want to make here, and it's a bit of the motivation of why we designed this based on Cocos, is the fact that if you look at the number of systems back in 2021 that were not using GPUs, you still had 3. Currently, it's 1, Fugaku, in the top 10. The number of systems in 21 that were using NVIDIA GPUs was 7. Today is 3. And 5 of them are using AMD GPUs, and now 1 of them is using Intel GPUs. So if you were, you put a lot of work to port your code to CUDA, now you're cursing in 5 different languages because it's very annoying to have to port again. So with that on mind, we made the conscious choice of using Cocos. So I highly recommend it. It's been a joyous ride in that sense. In the European infrastructure, we of course have large systems available. There's a variety of smaller systems. Mare Nostrum just left the top 10. It's now 11. And in Jülich, we will soon have Jupyter fully deployed. We have a test system already in place called JEDI, and this will exceed 1 exaflop anytime that we actually get it deployed. It's being constructed in France and will be shipped, essentially mounted to just plug in Jülich any day, pretty much. So we will not be number 1, but we hope to be number 2 in the world. So I'll show you some results with the test system that we have here. So never mind the legend of this plot. There's a lot of information here, but the point that I want to provide here is we've tested SERGHEI on all the systems available in Jülich, and we see the same kind of scaling behavior, including JEDI, which is a test system for Jupiter, is exactly the same nodes. It's just 48 of them and not 6,000 of them. But we get very, very good scaling. And very interestingly, we get about a factor 1.8 speed up relative to our previous generation GPUs, A100 GPUs, compared to these Grace hoppers now that we have. So that's without any optimization, just compile, run, and measure. So it's very auspicious that we'll have something in the order of a factor 2 speed up. And we've also tested the performance portability of SERGHEI across different GPUs. So here you have NVIDIA GPUs in blue and orange, AMD GPUs in green, and Intel GPUs in red in systems in the US. And again, so the point here is not which one is faster than the other one, because there's different generations of GPUs available in there. But the point is that the scaling holds, right? So the performance portability is really holding. The big effort in getting SERGHEI deployed in Frontier with its AMD GPUs, or in Sunspot, which is the precursor of Aurora, it's the test system for Aurora, was not really compiling SERGHEI. It was ensuring that we had the correct software stack. So it was more on the system side than on the code. All right, so let me show you some results and what we can do with SERGHEI. The first one that I will show goes back to these floods in Germany in 2021. I've shown you this figure before. Again, there's Jülich. Here's the area that was severely affected, but all the region was kind of affected. And I will focus on this area around Altenahr, where the death toll was by far highest. So there you have it. This is the area of interest. It's this small rectangle in here. And as I said before, if your area of interest is that small black rectangle, these big pixels are very much useless, right? They don't really help you very much. What does SERGHEI do? Well, we can run a simulation. This is the same small rectangle, but resolved at 1 meter resolution with SERGHEI. So you have to be a bit patient. If you could see it closely, you would see that the water on the stream is decreasing and increasing, but at some point you get the full flood wave and you see the propagation on all of these urban areas that are in the lower valley. Now, I would call your attention to the color scale. The water depth in the upstream parts was about 17 meters. So you can imagine what that does to your buildings, right? It was really catastrophic. And for comparison, here's the small black rectangle of the type of information that we currently generate in warning systems. So the claim that I would make here is we should be deploying these type of models to do early warning, right? Because they give you all the full information that you need. You may ask, well, do they actually perform well in terms of skill? Yes, especially at very high resolution. So there's a comparison of two different models, but I will just focus on the middle part of the figure here. The results that SERGHEI obtained versus the observations, which were measured after the flood. And these are just standard metrics that are used in flood modeling, basically. So I don't want to provide details. The point is they're all around 0.85 to 1, which is super good, basically. These are very good metrics. And you can see that they increase with resolution. So as we move from 10 meter resolution to 1 meter resolution, we get significantly better results. At which cost? Of course, that's the next question that pops up. Okay, there we go. Hold on. Yes, I will show that in a minute. Additionally, we also not get only the water depth, which is super important in terms of, kind of imagining the magnitude of the flood and conveying this to the general population, but we can get actually velocities and momentum. So if you use this type of map, which shows maximum momentum during the flood, you can estimate, where are the structures in danger because of structural collapse. You can compute forces. And at this resolution, we can translate these forces into individual buildings because we actually have information of the geometries of individual buildings. To further kind of push this point, you have a close-up here of this upstream part of the valley at 10 meter resolution, which, it kind of looks okay. You would say this is a good enough simulation. When you look at 1 meter resolution, you see that the buildings are much better resolved. And there's some areas which actually flood at 1 meter resolution. and don't flood at 10-meter resolution. The correct one is, of course, the one with highest resolution. That area actually flooded during the event. So there's a lot of added value, and as I said, this is how it looks in reality. So this picture here is looking upstream in this direction, and the picture below is looking upstream in this direction. You see these buildings here are these buildings that were destroyed. So this is kind of an interesting use of these models. We can provide information not only for early warning, but we can provide information also for insurance purposes, for example, of what were the flow conditions in that event. What about the computational time? So you have it here in absolute terms for SERGHEI, in particular on the red line, for different resolutions. But most interestingly is this time normalized by the duration of the event, because that's what really matters, right? So if it takes 5 minutes to compute or 1 hour, well, what does that mean in the context of for example, early warning? So we get essentially at 10-meter resolution a factor roughly 400. So 400 times faster than the real event. And at 1-meter resolution is a factor roughly 4. That's in the order of magnitude with a 100 GPUs. And here I'm not talking about, 20 nodes. So I'm not talking about 80 GPUs. I'm talking about 8. That's the scale of resources that is required. The point is we can do faster than real-time simulations at a very good resolution and with a reasonable amount of resources. I'm going to skip this because I have a similar figure for something else later that's much more interesting. We can provide, of course, much more information. We can provide the time to the maximum water depth, and we can provide lag. Essentially, how long will it take since we detect these discharges upstream that we have impact downstream? And again, what is very, very important about this is, as you would expect, this lag grows as you go downstream. That is no surprise to anyone. But what is very interesting is that the lag error significantly decreases with resolution. So this is, again, an argument. Why do we need these tools to work at high resolution and HPC? Because they provide us not only a much better representation of the flood event, much more fine-grained representation of the hydrodynamic conditions and of the buildings, but also much better timing information. And if you're managing this from an early warning point of view, this is critical. This is what you need to know. We've done extensive comparisons against the measured data, and essentially, again, I will not go here into a deep analysis, but we see, reasonable results for a fully uncalibrated model. And this is a very important point, because if you're going to do early warning for a flash flood, you have no time to do calibration. You deploy and you compute and you see how it goes. So you need to have more or less robust results without calibration, and that is reasonably the case. So we can improve let's say can decrease the scatter of these points that you see here by calibrating, but that it's kind of defeating the purpose of the exercise. That's why we don't do it. The next step is scaling this up, because one issue that you may have thought about when you saw the figure is that this requires to know how much water is coming in from the side, which of course you don't before the event actually happens. So a solution to this is, well, just scale it up to the whole catchment, because what you do know, more or less, you can also measure, is the rainfall that is occurring. So you have weather forecasts that give you an ensemble of potential rainfall fields, and you can have on the fly radar precipitation fields whenever this is available. This is, in fact, the case in Germany. So this area is covered by a few radars. So this is what I'm currently working on, is on scaling up this to this entire catchment. Catchment is about 900 square kilometers. It's not huge, but it's not small. And to give you an idea of what is the cost of this, if we solve this at 25-meter resolution, we can solve the event roughly 600 times faster than real time on one single node in jewels. If we take it to 1-meter resolution, that requires about 128 GPUs on jewels, with a computational time that is around 4 times faster than real time. So that tells us, well, with this generation of hardware, we maybe cannot do this for early warning at 1-meter resolution, but we can certainly do it at 2-meter resolution, where we can get in the order of 20 times faster than real time with a reasonable number of resources. So this is feasible. And it actually looks like this. For you to get an idea, this is a first experiment, which is a bit boring. These flashes of color that you see are the runoff being generated on the catchment. You see that what I was showing before was only this part here downstream. But in this exercise that I just showed you, as I said, it's just a computational exercise of having uniform rainfall on the entire catchment, which is thoroughly unrealistic because it's a very large catchment. And now I will talk a little bit about these plots. This is a very nice tool that we have in Jülich. It's called LLView, which provides you an automatic report of the usage of your resources. So you have the time of the job here, when this job was executed, and here you have all the GPUs that you used for that job. And the heat map shows you essentially the usage. So on average, you see this job used roughly about 70% of the GPU time, if you will, the capacity. It used up to 100% in some of those GPUs. And what is really interesting is the distribution. Some of them, let's see if I can do this. Yeah, some of them are underused. Some of them are more continuously used. And this points me back to the idea of better domain decomposition. There's a load imbalance. And when you look at the GPU power, which is a bit more responsive, you see at some points, even the highly used GPUs show a decreasing power, which means they're being underused temporarily, right? At some point, they're being heavily used, and then they're not used a lot. So this points us into the direction of dynamic load balancing and eventually into this idea of malleability. If we have these large differences in the compute effort that is being demanded out of the resources, we have the opportunity to be, let's say, more energy efficient, more energy compliant, to go in the direction of green computing. So for reference, this job costed about 400 kilowatts hours, which is what takes your refrigerator to run for about 2 months. So if that's a lot or not, I will not judge, but it gives you an order of magnitude, right, of the power that is put in there. I'm currently spinning this up into more realistic things. So we're using radar data to drive the catchment. We're computing the same thing. So we want to get the water depth, we want to get infiltration rates, the accumulated infiltration, and so on. And I have a nice animation that I can talk over. You have to be patient because it's a 3-day long event. So you will see now the real rain happening here. This is what the radars measured at 1 kilometer resolution, 5 meter frequency in time. So you see how the water depth starts to develop and goes away, which is very nice. You get sprouts of rain, parts of the catchment activate, and at some point you will see the core of the event. So now it's loading. You see that water is propagating in the middle parts of the catchment, although it's not raining anymore. And as the large part of the rainfall event, you actually see how much rainfall is being accumulated and how we develop now the full flood wave there. Again, this is all uncalibrated. There's, let's say, reasonable parametrization. That's the whole point of the exercise. Now, this we don't only apply to rainfall runoff problems in catchments. We apply to more classical river floods as well. This is just an example of a test that we did in the SERGHEI River in Italy. And the point that I want to make here is we're doing here long-term simulations. So this is a 2-month hydrograph that we're putting on the west side of the river. And the problem runs roughly about 220 times faster than real time, or if you will, 6 minutes per simulated day. So you can do very long-term things with this as well, with a reasonable number of resources. In this case, it's a single node in joules. From these tests, we learn a bunch of different interesting things. For example, I will take always this metric, this FTRT, which means faster than real time. And I just want to point you out here that the resolution has a big impact on this number. And this has to do with the temporal discretization of our integrator, right? It's an Euler scheme. So when we increase resolution, we have to decrease a time step. And there's no workaround. Whereas when we make the problem bigger, by, either if we put more cells, we can throw more GPUs, but we cannot make the time step larger. And this is the main bottleneck that we have. If we make the problem bigger by adding more area, we can throw more GPUs at it. It's not an issue. So we can use this information to generate analysis of different systems. This holds across different types of problems. So again, we have rainfall runoff problems. We see the same behavior of this time. And this gives us a lot of information. For example, for early warning, we could simulate multi-resolution ensembles where we do coarse simulations simultaneously with fine simulations, and the coarse ones will finish within minutes, while the fine ones are already computing and gaining a bit of time. This is information we can use. I will skip some of these plots. But not everything is really solved. So here you have another example of a large-scale river application in Spain, where there's a reservoir in the river here downstream. And this also creates numerical issues because of the large water depths in the reservoir, which can govern the time step. So when we get into these reservoirs, this is very boring. My point is the solution in the reservoir is not interesting to anyone, basically, but that's governing our computational effort. So we have to find smart ways to offset these costs. I will now very, very briefly give you a run through of the other modules in SERGHEI for you to have a complete picture. As I said, we recently published this subsurface flow module, and we went through the same exercise. Again, we took standard benchmarks from the literature. We did some very nice testing at different resolutions with different algorithms, and I will not provide the details here, but our results pretty much show that there's sufficient accuracy and robustness in our solver. We also are applying a kind of novel approach to solving Richard's equation, whereas everyone typically does this Newton-Raphson, let's say this Newton scheme that linearizes the system of equations and then does some kind of Krylov solver to solve the matrix. What we're trying to avoid is having to solve, let's say, executing the Krylov solver many times in the same time step, because this is a scalability bottleneck, basically. So we want to enhance the scalability. And so we've proposed this alternative approach, which is a predictor-corrector scheme. And we've implemented that on SERGHEI with kind of very nice results. So if we take, again, problems both solved on CPUs and GPUs, we see very good scaling. This is for a single node, but we can also look at it for many nodes. So you can see here, number of GPU nodes, we went up to about 400 GPU nodes in joules, with very good scaling, roughly at around 64, even 128 nodes. We have very good scaling for a relatively small problem that has 120 million cells. So it's an alternative. This is far less common. Most of the subsurface solvers do not do this approach, but they suffer much more from poor strong scaling. They have relatively good weak scaling, but usually don't have very good strong scaling. And because we want to do high resolution, we want to have this possibility of strong scaling. Another module that is in the works is this sediment transport module, and in more general terms, the advection dispersion module, which basically builds up on the shallow water equations and adds up this advection dispersion of equation of a scalar. This, again, enriches our hyperbolic structure, brings us some new source terms for erosion and deposition. And we're that picture doesn't look that bad, I promise. So if you look at it on the screen, you don't see those weird wiggles. That's a bit of pixelation. It's actually very smooth. And when you look at it a bit up close, when you look at, for example, the amount of sediment that you have suspended after a dam break, I also wanted to illustrate here what's the effect of resolution. So we're kind of enabling these very, very high resolution simulations also with sediment transport. And that's just for a close-up. Because these are lovely, very well resolved structures of the suspended solute or suspended sediment. We have not yet done very thorough testing of the scalability of this module, but we're essentially seeing the same behavior, and we're trying to understand what is the overhead by increasing the number of scalars, because it's essentially it doesn't come for free, but it doesn't add a full new solver by adding more and more scalars. Why do we do this? Because we want to be able to transport many substances at the same time, right? And we need to know how much more expensive it's going to be. This comes with new challenges when we go at very high resolution and deal with these, let's say, don't imagine a river, imagine a hill slope on which you put rain and you get some erosion. So I think this is easy to imagine in Cyprus. We get these kind of unstable, wiggly behaviors. Well, I'm pressing the wrong button. This kind of wiggly behaviors if we do a naive integration of our source term again. So we've had to move to an upwinded integration of our source term to restabilize this and get a good behavior. And this was interesting because this was the result of pushing this technology into higher and higher resolution. And my colleagues in Spain are applying this to erosion analysis on post-wildfire catchments. Essentially, place where you get a wildfire, all the vegetation is destroyed, and then you get rain, and this washes out all the organic matter and the soil, the topsoil out of it, creating, a problematic ecological situation. And this is basically being driven with SERGHEI. Finally, we have this Lagrangian particle tracking model, which is super simple. It's just an advection equation of a mathematical point. So you can imagine more or less how that works. The only difference from what we're doing from what everyone else is doing is we want to keep an Euler scheme that is tightly coupled with a shallow water solver. So we don't want to take snapshots that are many minutes or many hours apart and then interpolate with high order interpolators, but actually advect the particles at the same temporal resolution as the flux. The main reason for this is because we have these wetting and drying processes. So whenever the water dries out on a place, that particle deposits and doesn't move anymore. Whereas if we interpolate with long snapshots, we would have the particle moving. And this intermittency, this disconnectivity of the fluxes is crucial. We also want to do kind of more fancy things with this. This is the type of things that we are seeing now kind of every autumn in the Mediterranean basin. Flash floods, which transport cars and things like this. So we want to evolve this Lagrangian module into something that can represent this, or that can represent urban furniture being transported. So you actually see these are videos from the recent floods in Valencia in October. So there's a PhD student working on incorporating minimal physics to have this on top of our models. Currently, it's looking very auspicious. So we've done preliminary testing of how it performs with our Euler scheme or with Runge-Kutta schemes, and we've shown that Euler is sufficient, which is great because it's also cheaper. So that particle should be doing perfect circles, and it actually does very, very nicely. And we've tested this a little bit also with more real floods. So I hope you can see the little white dots that move around there, or don't move them. Now they move again on complex recirculating flumes and so on. So this is currently mostly under testing. We're also asking ourselves, there's something wrong there in the title. We're asking ourselves, what is the effect of introducing some kind of turbulence representation? Not a turbulence model, just a representation of a little bit of chaos, let's say, of dispersivity through a random walk model, and trying to understand what this does. The reason for this is that the very high resolution that we use pretty much eliminates all numerical dispersivity of the grid. So the particles follow super streamlined paths, which are actually not very realistic. Finally, we can apply this at catchment scale, put some rain, and see how these particles move. And what these particles can be, they may be seeds, they may be microplastics, they may be a variety of different things. And just for the fun of it, what happens if we put these particles on the same R flood that I showed before? You see those red dots propagating there. And actually, as I said, because we have this wetting and drying thing, when it dries off, they remain where they should be. And this is important if we want to understand the transport of objects. So the take-home messages I will not repeat. They're the same as the beginning. I hope this has painted a nice picture of what it is that we do and why it is that we do it and why we think it's worthwhile doing. And with that, I finish, hopefully not too delayed. And I thank you very much for your attention.
Thank you, Daniel. Very interesting presentation. I think we can take one or two questions and then we can move outside if anyone has a question.
So it was very interesting. I don't know if I got everything right, but you're modeling also stream flow with your Sumfrenon equations?
Yes.
So, and that's stable or?
Yes.
Okay.
Thank you very much. So how far do you think we are from replacing these LAMP models for flood prediction across Europe with more detailed, very high resolution models? And would you think that it makes sense to run coarser resolution for most of the time and then activate very high resolution when the weather prediction is favoring extreme weather?
So to the first question, I think we're very far from that, and it has nothing to do with science or the technical challenges. It has to do with the politics. This comes from my personal experience, let's say, trying to pitch these ideas like I've just pitched them to you to authorities who are responsible for flood management is much harder than pitching them to scientists. There is a certain reluctancy to move away from well-established systems Some of the reasons are good. You have something that runs, that you know how to operate, and that has been tested in time. But I think that's a bit of an excuse because you can run these things in parallel. You don't have to give up your previous systems. You can add on the new systems. And there's a certain reluctancy to that in my view, mostly comes from the idea of we don't want to worry about running a supercomputer. And then, of course, my answer is, well, that depends on how you define a supercomputer. If you want to run in your let's say, agency for nodes, that's probably sufficient to whatever purposes you want to do, because flood management is usually done rather locally, right? You don't want to manage an entire country. You want to manage your region of interest. And moreover, and more importantly, the approach in Europe is towards a federated HPC environment. And there is a lot of pressure, let's say, being put on Euro HPC that the access to these supercomputers can also be done on demand emergency basis. So that would completely offset the issue, right? You don't have to operate a supercomputer. You have it there, and we have to develop some protocols, and there's technicalities involved on how to deploy emergency simulations, not only for floods, but for volcanic eruptions and whatever you may think of as hazards, pandemics, for example. Regarding your second question, absolutely yes. That's, I think, what we should do, right? So when it's not raining, there's nothing to compute, very easy. When there's some forecast that says, there's some event, well, let's launch some coarse simulations and see what it says. If we see that it's important, we activate the next protocol, we launch high-resolution simulations. So absolutely. I mean, this can be staggered in a very smart way, and that should be the way forward, I think.
I have a final question. It's on the software development side of things. So you mentioned you're using Cocos. Can you provide a rough estimate on the development time saved from using Cocos rather than have to actually write CUDA or HEAP or OpenMP and all those things?
So let me answer your question from two perspectives. If I think of the perspective of developing a code from scratch, this is a SERGHEI perspective. If we had developed SERGHEI from scratch, let's say writing CUDA, I would say the reduction in development effort is easily a factor 2, at least. And the main reason is that debugging CUDA is much harder than debugging code that's running on your CPU, right? So if you write from scratch on CUDA and you're making mistakes, it's much harder to figure out than if you're writing your plain code. And if you want to run your CUDA code on the CPU, then it gets annoying as well. So that in itself, Cocos allows you to write the same code, test it on the CPU. It kind of works. Now you move it to the GPU, you get a couple of seg faults here and there. You realize I missed my Cocos inline function, and then all done. Then if you add to that, then the portability factor that you could move into HIP or into SYCL, then multiply that by a factor 2 for every language, I would say. So it's easily, a factor 8, a factor 10 or more. The second perspective is, what if you're starting from a code that already exists? Let's say in the best case, a C or C++ code that is already parallelized, say over OpenMP and MPI, and you just want to move it port it into CUDA. I would say that you would also get a very significant reduction, potentially a larger reduction even in your effort, because you can more or less simply translate your structures into the data structures of Cocos and trust Cocos to do the memory handling for you. That is with the assumption that you have something that has been parallelized already. If you have to parallelize it, then, well, it's on you. Yeah, but I would be very optimistic about the time savings. Yeah.
Thank you, Daniel, again.
My pleasure.